All right, if you're writing any Go code at all, you are absolutely going to face this choice. Should I use a mutex or should I use a channel? Today, we are getting to the bottom of this classic concurrency debate. And trust me, understanding the trade-offs here is one of the biggest keys to writing clean, efficient, and bug-free Go code.
So let's just dive right in. Look, this isn't just some academic debate. This is probably one of the most common questions you'll get in a Go technical interview. And your answer? Well, it tells the interviewer a lot about how deeply you really get Go's whole philosophy on concurrency. And to make sure you absolutely nail that answer, here's our game plan. We're going to start with the single most important concept, the golden rule of concurrency in Go. Then we'll dive into channels and mutexes using some really clear analogies. We'll also touch on a more advanced topic, mutex versus RWMutex, and we'll wrap it all up with a handy interview cheat sheet. Okay, let's get right to the punchline. Seriously, if you remember only one thing from this whole explainer, make it this right here. This is a simple idea that's going to guide like 90% of your decisions when you're writing concurrent code.
It all boils down to this. Are you handing off data from one worker to another, kind of like passing a baton in a relay race? If so, that is a job for a channel. Or do you have multiple workers that all need to access and maybe change the exact same piece of data, like a shared counter? That is a job for a mutex. Passing versus sharing. That is the fundamental difference.
And this difference perfectly captures Go's famous concurrency proverb. The language itself has a strong preference. It wants you to share memory by communicating. In other words, it wants you to use channels. That's the idiomatic, the Go way to do things. But it also gives you the tools to do it the other way around when you have to. And that's where mutexes come into play.
So let's start with Go's preferred method, channels. You can think of these as the plumbing system for your concurrent application. They're designed specifically for communication and orchestration between your Go routines. So what is a channel really? Well, you can think of it as a typed pipe. One Go routine shoves a value into one end, and another Go routine receives that value on the other. It's the core mechanism in Go that lets totally independent functions talk to each other safely without stepping on each other's toes.
This conveyor belt analogy is honestly perfect. Imagine one Go routine, we'll call it the producer, is just placing tasks on the belt. It has no idea who's going to pick them up, and it doesn't care. Then, way on the other side, you've got another Go routine, the consumer, that just grabs a task off the belt and gets to work. With every single handoff, the ownership of that task is clearly and safely transferred.
You know, what's really powerful here is that channels do so much more than just move data around. We use them to distribute work to a pool of workers, to signal when a job is done, or even to handle cancellations gracefully. And when you combine channels with Go's select statement, you can listen to multiple channels at once, orchestrating really complex workflows, kind of like a traffic controller at a busy intersection.
Okay, but what happens when you can't just hand the data off? What if you have some piece of state, some variable, that absolutely must be shared and accessed by multiple Go routines at the same time? Well, that's when you reach for a completely different tool, the mutex.
A mutex, which is short for mutual exclusion, is basically a lock. Its one and only job is to protect what we call a critical section of your code. That's the part where you're actually touching the shared data. It provides a simple guarantee. Only one Go routine can be inside that section at any given time. This prevents a nasty problem called a race condition.
This analogy just makes it crystal clear. Think of your shared data as a tiny, single-person bathroom. To get in, you have to grab the one and only key. That's what calling lock does. If someone else already has the key, you just have to wait in line. When you're done, you return the key by calling unlock, and that lets the next person in line have their turn. It's a really simple but effective way to guarantee exclusive access.
So where do you actually see this in real-world code? Oh, all the time. If you have a struct, and different Go routines might be trying to change its fields, you absolutely need a mutex. A classic example is building an in-memory cache. You could have tons of requests trying to read and write to that cache at the same time. You have to lock it to keep all that data from getting corrupted.
And here is a pro tip, and I mean this is absolutely essential for avoiding some really nasty bugs. Whenever you lock a mutex, your very next line of code should almost always be defer mu.unlock. The defer keyword guarantees that unlock will be called right before your function returns, no matter what happens. Even if your code panics, the lock gets released. This one little habit will save you from deadlocks that can bring your entire application to a screeching halt.
Okay, so you've got the basic mutex down pat. Now, let's level up a bit. For those of you who are aiming for more senior roles, you need to know about this crucial optimization, the read-write mutex. So remember our bathroom key? It's a totally exclusive lock. It doesn't care if you're just popping in to quickly look in the mirror, a read, or if you're, replumbing the whole thing, a write. Only one person gets in at a time, period. And that can be pretty inefficient if you have lots and lots of readers. A sync.RWMutex, on the other hand, is smarter. It's more like a library. It understands the difference between reading and writing. Think about it. Many people can be inside a library reading books at the same time, no problem at all. But if one person needs to go update the central card catalog, that's our write operation. The librarian has to lock the main doors, wait for all the readers to finish up, and let only that one writer in to do their work. So the rules are really simple. If you're just reading data, you use rlock. And multiple Go routines can get a read lock at the exact same time. But for writing, you use lock, and that's an exclusive lock that waits for all the readers to leave and blocks any new ones from coming in. This can be a massive performance boost for data that gets read all the time, but only written to once in a while.
All right, let's bring it all home. We've covered the core philosophy, we've looked at the tools, and we've even gotten into some of the advanced cases. Now, let's put together the perfect answer for that interview question.
Here it is, everything on one slide. Use channels when you're passing data and orchestrating Go routines, that's your conveyor belt. Use a mutex when you are guarding shared state and protecting a critical section, that's your bathroom key. If you can explain this clearly, you are going to be in fantastic shape.
And for the bonus points, here's how you handle the follow-up. When they ask, so why use an RWMutex? Your answer should be simple and direct. You use it for read-heavy workloads. It boosts performance by letting all the readers in at once while still giving you that exclusive lock for those rare write operations.
So now you have the framework. Pass data with channels, share state with a mutex. But the real magic, where Go's concurrency model truly starts to shine, is when you start asking, what happens when you need to do both? Combining these tools is how you build incredibly powerful systems. And that's a puzzle we'll save for next time. Keep building.